Hello everyone. So today's class is about tips and tricks on factorial experiment and confounding, and this will help to understand various type of MCQ problems. So let's start with the basic topics or the basic understanding on factorial experiment. Okay. Here we can see that in usual design like CRD, RBD and LSD, we are primarily concerned with the comparison of the effects of different levels of a factor like varieties of rice, varieties of fertilizer. So these are basically our factor. Okay, and we can take different levels of any factor. Let's say if we choose the varieties of rice, so this is one of a factor, and then we have to choose different levels of that factor to work with like CRD, RBD and LSD. That means here we deal with only one factor at a time. That means here we deal with only like varieties of rice or only like varieties of fertilizer. Okay, but we cannot deal with like 2 or 3 factor at a time. So that's why to deal with multiple factor or to deal with several factors at a time, we have to use the concept of factorial experiment. So in factorial experiment, or let's say factorial design, effects of several factors are investigated simultaneously. Now that means if a factorial design involves k factors with, let's say, levels p1, p2, pk, then it is called p1 cross p2 cross pk factorial experiment. Okay, so pk factorial experiment. Now if let's say the number of levels, so if let's say the number of levels of each factor in an experiment is the same, okay, then the experiment is called symmetrical factorial experiment. So this is called symmetrical factorial experiment. Okay, now but if let's say they are not same, then otherwise, so otherwise it is called asymmetrical otherwise it is called asymmetrical factorial experiment. Okay, now what does that mean? So it says that if the number of levels of each factor in an experiment is basically same. Okay, now what does that mean? That means, so that means if let's say if we have two factors like a and b and both have two levels, okay, so both have two levels, let's say a1 a2 and b1 b2, okay, so we can see that all the factors and each factor has equal number of levels. Okay, so that's why this type of experiment will be symmetric, or you can say like symmetrical factorial experiment. Okay, but if let's say a has three levels like A1, A2 and A3, and B has two levels like B1 and B2. Okay, so if A has three levels and B has two levels, so then this type of experiment, if in that experiment only A and B are the basically two factors, so this type of experiment are called asymmetrical factorial experiment. Okay, so now let's go to the next topic, which is on 2 to the power n factorial experiment. So what is 2 to the power n factorial experiment? Let's talk about this 2 to the power n factorial experiment. Now 2 to the power n factorial experiment means we have n factors, okay, and each and every n factor has two levels. Okay, that means let's say we have, so this implies that we have n factors, and then that n factors can be denoted by, let's say, a1, a2, an, or you can denote it by any other alphabets also. So we have n factors, and each factor has two levels. Okay, now these two levels can be denoted as like presence or absence, or this two level can also be denoted as like high or low. Okay, so mostly we denote these two levels by presence and absence, or we can write as high and low. Okay, so most of the time we do this. Now so let's start with, let's say, 2 square experiment. Okay, so in 2 square experiment we have, let's say, two treatments, or you can say like two factors, not treatments, so two factors a and b, and then a naught, b naught, which will be similar to 1 and which is basically denoted by 1. Now what does that mean? So a naught and b naught means, let's say a and b are two factors and each has two levels. Okay, so a and b are two factors and each has two levels. Okay, so the first level and second level are basically denoted by 0 and 1. Okay, so you can think of like 0 means absence and 1 means presence. Okay, so you can think of like that. So a naught and b naught, that means a and b both are absent, so that's why I'm taking this 1. Okay, so let's say the second one is a1 b naught. Okay, now what does that mean? That means a is present but b is absent, so that's why we can write this as a. Okay, and next one is like a naught b1, that means a is absent but b is present, and we can denote this as, let's say, b. Okay, similarly, let's say if we write a1 b1. Okay, so a1 b1 denote, that means a and b both are present. Okay, so if we denote 1 by presence, so a and b both are present. Now if both are present, then we can denote that by a. Okay, and we can also denote this using, let's say, a and b both, or let's say, so you can write as like both at first level. Okay, as 0 denote the first level, 1 denote the second level. Okay, or 0 denote the lower level and 1 denote the higher level. Okay, so a and b both at first level. Next, the second one, a is at the second level but b is at the first level. Okay, so a is at second level but b at first. So first means b at first level. Okay, so let's make this as B at first level. Okay, similarly this third one is like A is at first level but B is at second level. Okay, so A is at first level but B at second level. Okay, similarly this quantity we can write this as A and B. So as both has this 1 as index, so that's why A and B both are at second level. Okay, so A and B both at second level. That means both are present. So if we just denote 0 and 1 by presence, so absence and presence, so then we can call that A and B both are present. Okay. Now sometimes in MCQ question it is given that like a note number 1, the effect, so the effect of capital A at the first level B naught of B, and what will be that? Okay, that means the effect of A, we just have to calculate the effect of A at first level of B naught or first level of B, okay, which is B naught. Now what does that mean? So how can we get the effect of A? So effect of any factor can be evaluated by, let's say, presence of that factor minus absence of that factor. Okay, so we can get the effect by checking the presence minus absence of that effect. So let's say effect of A, which is, let's say, A1, which denote the presence of A. So we can define this as presence of A, as the index is basically 1. So presence of A where B is at the first level, that means B naught, okay, minus absence of A, which is basically A naught at the first level of B. Okay, so that's why this value A1 B naught, that means A is present but B is absent, so obviously that will be A, and here A and B both are absent, so that's why we can write this as 1. Okay, so the effect of A at the first level of B naught or first level of B is B naught, then we can write in this way that the presence of A minus the absence of A at first level of B. Okay, similarly Similarly, let's say number 2, the effect of, let's say, A, or let's say the effect of A, but at the second level, let's say B1 of B. Okay, that means B is at the second level and we just have to calculate the effect of A. So simple, effect of A means presence of A minus absence of A. So presence of A minus absence of A, but at second level of B. So that's why B is at second level. Okay, and A1 B1 is basically AB, as A and B both are present. A naught, that means A is absent but B is present, so that's why it will be like minus b. Okay. Now the next part is how can we calculate the main effect of AB and AB. So as we are working with two square design, so that's why the main effect, so the main effect of, let's say, A. Okay, a shortcut technique to solve this type of problem. So as we are working with two square design, okay, so that's why, so it will be 1 by 2 to the power 2 square minus 1, which is basically 1 by 2, and then so we can write as 1 by 2, and then we have to calculate the main effect of A. So that's why we can take A minus 1 and then B plus 1. Okay, so then what will be the main effect of B? The main effect of B will be 1 by 2 into A plus 1 but B minus 1, as we have to calculate the main effect of B. So that's why we have to take the part B minus 1. So I am not proving this part, as this proof is obviously not very much difficult, but in this context I am not proving that part, as this is only for the MCQ purpose. So to find the main effect of B, we just have to take B minus 1 and all other effects, that will be, let's say, plus 1, like A plus 1, and if let's say C comes, then that will be C plus 1, but only B minus 1, as we have to calculate the main effect of B only. Okay, now let's go to the next part, which is the main effect of AB. Okay, so here you can see that A and B both are present, so that's why we have to take A minus 1 and B minus 1. Okay, that means if we have to calculate the main effect of any factor combination or like any interaction, then if A and B both are present, we just have to take A minus 1 and B minus 1, and if for, let's say, for only A, we have to take A minus 1 but B will be plus 1. Okay, so simple calculations. Now let's go to the topic, which is 2 cube factorial experiment. So in the similar way as 2 square, so let's go to 2 cube factorial experiment. Okay, so in 2 cube factorial experiment there are 3 factors. Okay, so 2 cube means what? 2 cube means there are 3 factors, and each factor has 2 levels. Okay, so each factor has 2 levels, so that's why it is 2 cube factorial experiment. Okay, that means, let's say, if we have the factors A, B and C, then each and every factor has 2 levels. So that means, let's say, 0 1, 0 1 and 0 1. Okay, now if we want to calculate the main effects of A, B, then C and then A, B, C, so then the main effects of, let's say, A, so that will be 1 by 4, as we have 2 cube, so that's why 2 cube minus 1 will be 4. Okay, so we have to take 1 by 4, so 1 by 4, then so here A is present, so that's why you have to take A minus 1, but all other quantities will be plus 1, that means B plus 1 and C plus 1, as we have 3 factors A, B and C. Okay, so then the main effect of B, so as we have to calculate the main effect of B, so that's why B will be minus 1, but all other quantities will be plus 1, that means A plus 1 and C plus 1. Okay, so let's talk about ABC. Okay, so if ABC, each and every one is present, that means A will be minus 1, B will be minus 1 and C will be minus 1 also. Okay, so simple calculation. So here this AB and you can call that C, so these ABC are called main effects, and these ABC, this BC, CA and everyone, So these are called interaction effects. Okay, so A, B, C are basically main effects and all others are basically the interaction effects. So now let's go to the next topic, which is confounding. So let's start the topic, which is confounding. And so what is confounding? So let's start with the basic concept, which is what is confounding. So let's say if we have 2 to the power 5 or let's say 2 to the power 6 factorial experiment. So why should we use the concept of confounding? So if we have 2 to the power 5 or 2 to the power 6 factorial experiment, then we have so 2 to the power 5 is basically 32 and 2 to the power 6 is basically 64. So 32 and 64 treatment combinations. Okay, so 32 or 64, even if we take let's say 2 to the power 7 or 2 to the power 8, then the values will be larger, obviously. Then what happens? Then the variation, so then the variation within replicates okay, so then the variation within replicates tends to increase. So tends to increase. Okay, and why? As the number of treatment combination increases, so obviously the number of plots in, or let's say number of plots in a particular experiment or particular replicate obviously increases. So that's why we just have to minimize this number of plots, or let's say to take more blocks. Okay, so that's why now which results a larger error variance. Okay, that means if we have 2 to the power 5 or 2 to the power 6 factorial experiment, but if we don't use the concept of confounding, then the error variance will get larger. So that's a simple concept. So here comes the concept of confounding. Now confounding can be divided into two categories mainly. One is complete confounding and the other one is partial confounding. Okay, so let's start with complete and partial confounding. So complete and partial confounding. Okay, so what is complete confounding? So if the same set of effects is confounded, so same set of effects is confounded in all replicates. Okay, so if we have let's say 4 or 5 replicates, so if we have let's say 4 or 5 replicates, and in each and every replicate let's say AB, the effect AB is confounded. Okay, that's why then we can say AB is confounded on each and every 4 replicate. So that's why that experiment will be a complete confounding. Okay, now if then we call that as complete confounding. Okay, but if we have let's say 4 replicates, but in first replicate AB is confounded, in second replicate let's say BC is confounded, in third replicate let's say CA is confounded, okay, and in fourth replicate let's say ABC is confounded. Okay, Even if let's say this can also occur, like in first and second AB and BC confounded, and in third and fourth both where ABC is confounded. Okay, so obviously it can happen. So this is a case of partial confounding. So partial confounding means if in different replicate, or in, let's say if we take 4 replicates, so in different replicate at least more than one treatment combination confounded. That means if, so in the complete confounded case we can see that AB is confounded in each and every replicate, but in partial confounding at least more than one different treatment combination confounded in different replicate, then you can say that partial confounding occurs. Okay, so if different sets of, so if different sets of interactions are confounded, so different sets of interaction are confounded in different replications, then it will be partial confounding. Okay, that means, so I have told you that if you have, let's say 4 replicate, so let's have an example for that. So if we have, let's say 4 replicate, so replicate 1, replicate 2, replicate 3 and replicate 4. Okay, and each and every replicate, in each and every replicate AB, the effect AB is confounded. Okay, now this is basically a case of complete confounding. Okay, so this is basically a case of complete confounding in each and every replicate if the same effect is being confounded. But let's say in first replicate AB is confounded, in second replicate BC is confounded, in third replicate let's say AC is confounded, and in fourth replicate ABC is confounded. So this is a case where in different replicate different treatment effects, or different treatment, let's say we can say like different interactions being confounded. So that's why this is a case of partial confounding. Even this is also a case of partial confounding. Okay, so that means if at least in 2 different replicate we have 2 different treatment combination, then we can say like this is partial confounding. So this is partial confounding. Okay, now to do this complete confounding and partial confounding, we just have to know the idea of key block. So what is key block? So let's go to the So here comes the concept of key block. Okay, so to do complete and partial confounding, we just have to understand what is key block and how can we construct the key block. So first of all, key block can be thought of, so key block can be thought of as a generator. Okay, so as a generator of other blocks. Okay, so that's why it is called a key block, or you can say like principal block. Okay, so key block and principal block both are same. Now so we can write this as in a replicate, so obviously in a single replicate. Okay, now key block always, so key block always has that treatment combination. Okay, so key block always has that treatment combination where all the factors is so key block always has that treatment combination where all the factors is at its lowest level. Okay, that is, or you can say like key block always has a treatment combination, so has that treatment combination, no, always has a treatment combination where all the factors is at its lowest level. So that's obviously a good point. And why? That means, let's say for example, if we have 2 to the power 3, so 2 to the power 3 factorial experiment. Okay, and let's the key block, so the key block is like 1 and then AB, BC and CA, suppose. So this is my key block. Okay, now this 1, as we have 2 factorial experiment, so that's why this 1 is basically a notation which is used in place of A naught, B naught and C naught. So A naught, B naught and C naught is basically denoted by this 1. And why? So A naught, B naught, C naught means the A, B and C are basically at its lowest level. So 0 is obviously the lowest level and 1 is basically the highest level, as this is a 2 experiment. So that's why each and every factor has 2 levels. So 0 is the lowest level, 1 is the highest level. So each and every factor at its lowest level. So then we denote this as 1, and 1 obviously or a necessary member of the key block. Okay, so each and every key block must contain the value 1. So next discuss some key points which you should keep in mind when you have to construct the key block. Okay, so let's start with some keynote. Okay, so principle, or you can say like key block, is always, so always constructed by taking even number of letters or no letters common from that treatment combination which we want to confound. Now what does that mean? So let's have an example for that. Suppose, for example, we want to confound, so we want to confound, let's say, AB. Okay, so then the key block will be, so then key block will be, so the key block will be 1, then AB, then C and ABC. Okay, so if we take, let's say, 2 cube factorial experiments, so then we can do this. Okay, so for 2 cube experiment, now we can justify the keynote here. So as you can see that we want to confound AB. Now we have to take, or we have to construct the key block taking no common or even number of common member from AB. So here we have no common member from AB, so we can no letter common with AB, obviously. Okay, so no letter common with AB, or we can call it like no letter common with small ab, as we denote this as small ab. Okay, so when we construct key block, we can denote capital AB by small ab to take the common members. Now in the second part, so we can see that if capital AB is denoted by small ab, so even number of common member or even number of common letter with small ab, as in small ab and this ab we have AB both are common, so that's why 2 common members. So that's why we can say like even number of common letters, so even number of common letters with AB. Okay, now C, so C has no common letter with AB, so that's why this is no common, or you can say like no common letter with AB. And ABC, so ABC and AB, or you can say like ABC and AB, so both has 2 common letter which is A and B, so that's why even number of common letter. Okay, so even number of common letters. Okay, so even number of common letters with AB, so that's why in this way we can construct the key block. Okay, so always try to remind that key blocks has those treatment combinations which has no common or even number of common with the confounded effect. Okay, so now let's go to the next topic, which is, so let's talk about 2 to the power n factorial experiment. So 2 to the power n factorial experiment in 2 to the power k blocks. Okay, and this is usually written as So this is usually written as 2 to the power n comma 2 to the power k, and this is the universal notation. So at 2 to the power n basically denote we have n factors, each and every factor has 2 levels, okay, and all of these total factors are divided into 2 to the power k blocks, okay. Now, so why should we use this concept? So we have worked with 2 to the power n, we have worked with the factorial concept, so why should we work with this concept? Okay. So in experiment, with, let's say, a large, so in experiment with a large, or can say like larger number of factors, more blocks per replicate, okay. So that means in a single replicate we need more blocks. If, let's say, if the value of n increases, okay, so if the value of n increases, then 2 to the power n will also increase, simple. And if 2 to the power n increases, then obviously in a single replicate the number of blocks will increase, okay. So more blocks per replicate are required. So you can call that, okay. Now to keep the block sizes small, so to keep the block sizes small, we apply this method, okay. Now if you don't know the concept of, let's say, replicate block or these things, so I'm just drawing a diagram. So let's say this is my replicate 1, okay. So replicate, or you can say like repetition. So in statistics or in design of experiment concept, we call replicate, or we call repetition as replicate. So this is my replicate 1. Now so we divide the replicate into 2 block, okay. So the first one, so this first one is basically block 1, and the second one is basically block 2, okay. Now we can divide each and every block into different sub parts, okay. So now the sub parts of each and every block, so these sub parts are called plots, okay. So the whole thing is replicate. These 2 dividers are basically the blocks, 2 blocks, and each and every block is divided into different plots. So these small boxes are called plots, okay. So let's try to remind that if we have, let's say, 2 to the power n comma 2 to the power k factorial experiment, so let 2 to the power n factorial experiment conducted in, let's say, 2 to the power k blocks of equal sizes. You can see that. So this block 1 and block 2, both the blocks has equal size. So each and every block has 4 plots, okay. So both the blocks have equal sizes. So equal sizes per replicate, okay. So per replicate means for each and every one replicate, then number of plots in each block. So number of plots in each block means, so here you can see that we have 4 plots in each block, okay. So the number of plots in each block will be 2 to the power n by 2 to the power k, which is 2 to the power n minus k. Okay, so if we have 2 to the power n factorial experiment, that means if we have n factored, each and every factor has two levels, and we have distributed these 2 to the power n factors like 2 to the power n treatment combination into 2 to the power k blocks, then each and every block, so each and every block will have 2 to the power n minus k plots. That means we have 2 to the power n minus k treatment combination in each incomplete block. So these blocks are called incomplete blocks. So these are not complete blocks. And why these are incomplete blocks? As all the treatment combination are not in each block. Okay, so let's say if we have 2 cube, so if we have 2 cube, so let's say if we have n equal to 3, then we can have like 1, then a b, a b, and the other block can be like, let's say c, ac, bc, and abc. Okay, so obviously we know that if we have 2 to the power 3 factorial experiment, so then all possible treatment combinations are basically 8. Okay, or you can say like all possible treatment combinations are 2 cube minus 1, so abc and abbcca and abc. Okay, so these are the all possible treatment combinations, so not 8. So these are the all possible treatment combination, but these all treatment combinations are not in a single block. Okay, so in block 1 we have half of the portion, and in block 2 we have half of the portion. Okay, so that's why we call these blocks are incomplete blocks. So these are not complete blocks. So if this one is a complete block, then it will constitute all the treatment combinations like a b, ab, ac, bc, and everything. Okay, so that's why it is incomplete block. So we have, so we can tell like we have 2 to the power n minus k treatment combination in each incomplete block. Okay, so we have 2 to the power n minus k treatment combination in each incomplete block. Okay, so here you can see that, so we have 2 cube experiment. Suppose we have 2 cube experiment, and we want to distribute this in 2 blocks. Okay, so we want to distribute in 2 to the power 1 blocks. Okay, that means 2 to the power n is basically 2 cube, and we want to distribute this in 2 blocks. So 2 to the power k is basically 2 to the power 1, so 2 blocks. So then each and every block will contain 2 to the power n minus k. So 2 to the power n minus k, so here n is basically 3 and k is basically 1, so 2 to the power 3 minus 1, that means 2 square. Okay, so each and every incomplete block will have 2 square, that means 4 treatment combinations. Simple. Okay, and another point you have to keep in mind, if you have like 2 to the power n factorial experiment conducted in 2 to the power k blocks, then 2 to the power k minus 1 confounding effects. So there are 2 to the power k minus 1 factoring effects which are confounded among the incomplete block differences. Okay, so I'm not talking about these incomplete block differences, so that's obviously a theoretical concept, but for MCQ purpose we don't need this concept. So always try to remind that if we have 2 to the power n comma 2 to the power k model, then 2 to the power k minus 1 effect or 2 to the power k minus 1 treatment combinations will be confounded. Okay, obviously in each replicate. So in each replicate. Okay, so always try to remind that in each replicate. Now let's have some example on that. So first example, so let we have 2 to the power 5 comma 2 square design or 2 square factorial experiment. Okay, now that means we have 2 to the power 5, so we can call it as 2 to the power 5 factorial experiment, or like if we have 5 factor with each and every factor has 2 levels. Okay, so that is 2 to the power 5 experiment in 2 square blocks in each replicate. Okay, so then we know that we just have proved that when, so this is 2 to the power k, so 2 to the power k minus 1, that means 2 square minus 1, so then 2 square minus 1, which is 3. Okay, so then 3 effects will be confounded. Okay, and obviously in each replicate, in each replicate. Okay, so note that, now note that if, let's say, if we have 5 factors, okay, so that's why we have 2 to the power 5 minus 1 treatment combinations. So if, let's say, A, B, C and ADE confounded, okay, so if ABC and ADE confounded, then their general interaction means, so then their general interaction which is, so general interaction is basically ABC cross ADE. Okay, so if we simply multiply this, we can get like A square then BCDE. Okay, but it is a 2 to the power 5 factorial design, so that's why each and every design has 2 level. We just have to take the powers, which is modulus 2. So we just have to consider the power modulus 2. So if we consider the power modulus 2, so each and every powers are basically 1 for BCDE, but for A it is 2. Now if we take modulus 2 means if we divide by 2, we have to take the remainder only. So if we divide the power of A by 2, the remainder will be 0. So that's why A will be vanished. Okay, and if we divide the power, all the powers of BCDE by 2, and if we take the remainders, so all the remainders will be 1. So that's why the general interaction term will be BCD. So the simple procedure is, if we just multiply these two quantities and if we get anyone or anyone's power 2, then we just have to ignore or we just have to delete that later. Okay, so that's called the general interaction. So then BCDE will also be confounded. Okay, Now there are some important points you have to remind regarding the orthogonal treatment combination. Okay, so let's talk about orthogonal treatment combination. Okay, so or you can call it as combinations. So based on this orthogonal treatment combination, we have a MCQ question on Delhi University. Okay, so points to be noted. So first point, if we have 2 to the power n comma 2 to the power k, so if we have this type of experiment, then we have n treatment, that implies we have n treatments, or you can say like n, so obviously you can call this as n treatment with 2 levels each. So n treatment with 2 levels each in 2 to the power k blocks, or you can tell that, like you can say like n factor with 2 levels each in 2 to the power k blocks. So both are similar. Now number 2, the second question or the second point is each block size. So each block size is basically 2 to the power n minus k. So we have just discussed that part. So each block size is 2 to the power n minus k, or particularly you can say that each incomplete block size is basically 2 to the power n minus k. Okay, so those blocks are basically incomplete blocks, those are not complete blocks. So those are basically incomplete blocks. Okay, now the third point, so third point is total number of, so this sign or this symbol means number of, so total number of confounded effect is basically 2 to the power k minus 1. Okay, then the fourth point, so always try to remind all these points. Okay, and this is very important for the examination. So the fourth point is if any two interaction or like interactions, so if any two interactions are confounded, okay, so if any two interactions are confounded, then they are generalized interactions, then their generalized interactions so then their generalized interaction are also confounded, are also confounded. Now what does that mean? So let's have an example for that. So let's say that is if, let's say AB, so AB and CD confounded. So if we get that AB and CD confounded, okay, so then their general interaction, that means AB into CD, so that will be ABCD will also be confounded. Okay, so then ABCD will also be confounded. Now let's go to the next point, which is point number 5. So fifth point. So fifth point tells us that the number of independent contrasts. Okay, and we can see a question on, let's say, I think on Delhi University, or yes, obviously from Delhi University. I will discuss that question later, but that question is basically on this point. number 5, the number of independent contrasts out of 2 to the power k minus 1 is basically k. Okay. So what does that mean? That means, so let's have an example for that. So the number of independent contrast out of 2 to the power k minus 1 contrast is basically k, and rest are obtained, so rest are obtained as generalized interaction. Okay, so generalized interactions. Now what does that mean? So for example, let's say the key block is basically 1 AB CD and ABCD. So this is basically the key block. Okay, now this AB, so this AB and CD, so these two are basically independent contrasts. Okay, so this AB and CD, so these, let's say you can say like AB and CD, so this set is independent, but this set which is AB, CD and ABCD, this set is dependent. Okay, so this set is independent, but this set is dependent. Okay, and why? As ABCD is constructed from AB into CD or AB interacted with CD. So this is called the generalized interaction. So we can see that if we have like 2 to the power 4 experiment, so ABCD, if we have ABCD, then if we have 2 to the power 4, and so 2 to the power 4 is basically equivalent to 2 to the power n, and in the key block, so in each block we can see there are 4 members, so that's why 2 to the power k, 2 to the power n minus k is basically equivalent to 2 square. Okay, as we know that 2 to the power n minus k is the number of member or number of plots in each block. Okay, so this is 2 square, so that means n minus k, so n minus k is basically 2 and n is basically 4, so k will be 2. Okay, so k is equal to 2. Now if k is equal to 2, this fifth statement says that the number of independent contrast out of 2 to the power k minus 1 is basically k. So for this case, for 2 to the power 4, so for 2 to the power 4 comma 2 square factorial experiment, the number of independent contrast are basically 2. Okay, as the value of k, is basically 2. Okay, so and what are those independent contrasts? So those independent contrasts are basically these AB and CD. So these two are independent contrast. Okay, and the generalized interaction is ABCD. Okay, so simple. And let's go to the next point, which is number 6. So let's go to the next point, which is number 6. Number of effects, so number of effects getting confounded automatically. Okay, so getting confounded automatically is 2 to the power k minus 1. So let's have an example for that, otherwise you cannot understand this properly. So for example, let key block in, so key block in, let's say 2 to the power 4 experiment is, so the key block is basically 1 AB CD and ABCD. So this is my key block. Okay, so 2 to the power 4, which is equivalent to 2 to the power n, so 2 to the power n is basically equivalent to 2 to the power 4, and in each block we have, so in each block we have 4 members. Okay, so that's why we can call 2 to the power n minus k as 4, or you can call this as 2 square. Okay, so that's why the value of k is basically 2. Okay, so there are 2 independent contrasts. So independent contrasts are basically AB and CD. Okay, so there are 2 independent contrasts. Okay, and it is given that the number of effects getting confounded automatically. Okay, so which effect getting confounded automatically? So this ABCD. So if AB and CD confounded, then ABCD will automatically be confounded. Okay, so that's why 2 to the power k minus 1. So 2 to the power k minus 1. So what will be the value of that? So 2 to the power k, so 2 to the power k is basically 4, so which is 2 square minus 2 minus 1, and which is exactly 1. That means only one effect or one treatment combination will be confounded automatically, and that treatment combination in our example is basically ABCD. Okay, so that is ABCD. Now let's have some example. So first example, in, let's say 2 to the power 4 comma 2 square experiment designed confound the interaction AB and CD. Okay, so confound the interaction AB and CD completely with blocks. Okay, and find another confounded effect. Find another confounded effect. Okay, so first of all we just have to construct the key block, and which can be constructed taking only no common or even number of common member from the confounded effects, or from the effects which we have to confound. Okay, so the key block, can be constructed like, so we have to confound AB and CD both. Okay, so that's why if we take no common member, then 1 will be that member. So 1, obviously no common member with AB and CD. Now even number of common member with AB is basically small ab. Okay, and even number of common member with CD is basically this. Okay, and even number of common member as we have, so we have 2 to the power 4 comma 2 square design. So that's why, as we have 2 to the power 4 comma 2 square design, so the, you can say like, so the block size, okay, So the block size, will be, block size will be 2 to the power 4 by 2 square, and which is 2 square, that means 4. Okay, so the block size will be 4. Block size means, so how many member will be in the key block? So the number of member in the key block will be 4. So that's why we have to take ABCD as the last member of the key block, as ABCD has even number of common member with AB and even number of common member with CD. So CD and CD, so these are basically the common members. Obviously these are even number of common letters. Okay, now how can we construct the other blocks? So the simple idea is, just let's choose a treatment combination which is not present in the key block, and let's say that treatment combination is basically A. Okay, so then multiply the key block with A. So if we multiply this, then we get A. If we multiply this, then we get A square B. But I have told you that if we get A square B, it will be converted to just B. Okay, so if any value, let's say if we have 2 to the power 4, that means 2 to the power 4 or 2 to the power n factorial design, then if the power gets 2, then all the letter, or let's say if we get A square, then this letter A will be vanished. Okay, so we will get only the value B. So if the power gets 2, or if the power is 2, then that corresponding letter will be vanished. Okay, so if we multiply each and every member of the key block by A, so obviously key into A, then we get A, then we get B, which is A square B is basically B, A into CD is basically ACD, and A into ABCD is basically A square BCD, but A square will be vanished, so that's why BCD. Okay, now let's choose another member. So we have chosen A, which is not present in the key block, so let's choose another member which is not present in the key block. So let's choose B. Okay, so then key into B, so 1 into B is basically B, AB into B is AB square, but B square will be vanished, so only A, then B, C, D, and if we multiply this quantity with B, then we will get A, B square, C, D, but I have told that if the power is 2, then corresponding letter will be vanished, so the ultimate result will be A, C, D. Okay, next key into, so let's choose another member, let's say C, which is not present in the key block. Okay, and which obviously which has not chosen in, let's say, in the previous blocks. So C, so if we multiply 1 by C, so this is C into 1 C, and then A, B, C. So if we multiply this quantity by C, we will get C square D, but C square will be vanished, so that's why only D. So this will give A, B, C square D, but we have to take only A, B, D, as C square will be vanished. Okay, so we have 2 to the power 4 design. So obviously 2 to the power 4 design means we have 16. So we can say like 16 minus 1, 15 treatment combinations. So obviously we have 15 treatment combination, just excluding this one. Okay, and the other confounded effect, so AB and CD is basically confounded, and the other confounded effect is ABCD. Okay, so ABCD is also confounded. Now let's have another example. So let's have another example. So let's say in 2 to the power 4 design, it is given to us a block is 1 AB, CD and ABCD. Okay, so it is given to us a block is 1 ABCD ABCD. Now if any block is given to us and that blocks contain the value 1, that means that block is a key block. Okay, so if the key block is given to us, then it's okay. But if the key block is not given to us, if let's say any other block is given to us, then we just have to convert that block into a key block. So I'll do that on the next problem. Okay, so let's solve this problem first. So here the number of treatment combination is basically 2 to the power n, which is 2 to the power 4. Okay, so this is 2 to the power 4 design. Okay, now we can see that in each block we have 4 members. That means the block size is basically 4. So block size, which is 2 to the power n minus k, is exactly 4. 4 means 2 square. Okay, so the value of the k, that means the number of block. So number of blocks are 2 to the power k is basically 2 to the power 2. We can easily solve n minus k is equal to 2 and n is equal to 4. So k is obviously equal to 2. So 2 to the power k will be 2 square. Okay, so number of blocks are 2 to the power k, which is 2 square. So the number of confounded effect, will be, so hence 2 square minus 1, that means 2 to the power k minus 1, which is 3. So 3 effects will be confounded. Okay, so 3 effects will be confounded. Okay, and these 3 effects are, so the key block is given to us. So that's why we know that key block is constructed taking no common or even number of common member from the confounded effects. Okay, now we have 2 to the power 4 design. So the treatment combinations are like A, B, C, D, A, B, C, D and everything. Okay, so from among them we can tell that AB, the confounded effects, so confounded effects are, basically AB. Okay, as AB has even number of common member or no common member. So with 1 and CD it has no common member, and AB and ABCD it has even number of common member. Then CD and ABCD. So these are the basically 3 confounded effects. Okay, now let's go to the another problem. So let's go to the another problem. So in the previous example we can see that the key block is given to us. Okay, but the problem is if the key block is not given to us, if a block is given to us which is not a key block. So let's have an example for that. So let's say if in 2 to the power 4 experiment a block is basically, let's say AB, AD, so AB, AD, CD and BC. So it is given to us. Okay, so obviously this is a block and which is under 2 to the power 4 experiment. Okay, now this is not a key block. So if we cannot get, or if we don't have the key block, we cannot assure or we cannot surely tell about the confounded effects. So that's why we just have to construct the key block first from this block. Now how can we construct key block from this block? So here 2 to the power n is basically equivalent to 2 to the power 4. You can see that the block size is 2 square, which is 2 to the power n minus k. block size means the number of members in the block. Okay, so 2 to the power n minus k. So that's why k is basically 2. Okay, now if k is 2, so obviously 3 effects will be confounded. So 2 to the power k minus 1, which is 2 square minus 1, 3 effects will be confounded. Okay, now we just have to find those 3 effects. Now to find those 3 effects, we just have to first construct the key block. So first construct the key block. Okay, so how can we construct the key block? So here you can understand the block is given to us is basically AB, AD, CD, BC. Okay, so if any of this type of block is given to us, the easiest way to construct the key block is just multiply each and every one of them by any one of them. So let's choose AD. Okay, so we can multiply each one of them by AD. Okay, so the key block will be, first of all, so if we multiply AB by AD, so if we multiply AB by AD, we will get A square BD. Okay, but it is a 2 to the power 4 design, that means here we have 2 value. So that's why if power gets 2 or if the power is 2, that letter will be vanished, so only BD. Okay, so we will get only the value BD. So the first member in the key block is basically BD. Okay, now if we multiply AD by AD, so if we multiply AD by AD, it will be A square D square. So all the powers are basically 2. So that's why it will be completely vanished and it will give the value 1. If we multiply CD by AD, okay, so we are multiplying this whole block with AD. Okay, so if we multiply CD by AD, then we get A into C, as we get D square will be vanished, so A into C. Now if we multiply this BC with AD, then we will get ABCD. As you can see that if one is present in any block, that block is obviously a key block. Okay, so that's why to get this one, we just have to multiply this block with any one of these member. So if we want to multiply, let's say, by CD, you can also do that. Okay, so first we have to construct the key block, then only we can get the confounded effects. Now we have to check which treatment combination has even number of common and no common with the key block members. So if we choose, let's say, BD, so BD has even number of common member with this, no common member with this, no common member with this, and even number of common with this. So obviously even number of common or no common member, so BD must be confounded. Okay, similarly AC, so if we choose AC, so AC has no common member, so here also no common member. AC has even number of common member, and here also A and C, so even number of common members. So AC also confounded, and AC and BD are basically independent, so they doesn't have any common members. So AC and BD are basically independent, so that's why their interaction, which is ABCD, so it will also be confounded. Okay, so the 3 confounded effects are this. Okay, so simple. If let's say the key block is not given to us, we just have to convert that block into the key block, then only we can get the confounded effects. Now let's go to the next concept, which is concept of partial confounding. So what do you mean by partial confounding? So I have told that partial confounding means in each and every replicate, or let's say at least in 2 different replicate, we have different number of confounding effects. So let's have an example for that. So let's say we have replicates like 1, 2, 3 and 4. So we have 4 replicates. Okay, and in each and every replicate we have 2 blocks. So let's divide each and every replicate into 2 blocks. Okay, so then let's say the first block is, so first block so these are the confounded effect. Okay, so let's say in first replicate, so in first replicate we have to confound AB. In second replicate we have to confound AC. Okay, in third replicate we have to confound BC, and in last replicate we have to confound ABC. Okay, so this is a case of partial confounding. We can see that in different replicate all the different, let's say, treatment combinations are being confounded. Now here if AB, so if we want to let's say confound AB, then the key block, so if we choose this as key block, so the key block will be constructed like in this way: no common and even number of common letter with AB. So let's say no common letter is basically 1. So all the key block will have the value 1. Okay, and no common member with AB. So no common member with AB means, so we can see that we have up to third order interaction. So that's why C is basically member which has no common letter with AB. Okay, so 1 and C are the necessary member of the key block. Now the other member, even number of common member with AB, which is basically AB and ABC. So AB has even number of common member with AB. ABC also has even number of common member with AB. Okay, so this is the key block. So I will construct this second block later. So let's go to the next replicate. So AC, so we have to confound AC. So we have to take no common or even number of common member with AC. So no common member is basically B, and even number of common member AC itself and ABC. Okay, now the next one is no common member A, even number of common member BC and ABC. Okay, next for ABC, no common member is basically 1, then even number of common member is AB. AB and ABC has even number of common member. BC and ABC has even number of common member, and CA and ABC has even number of common member. Okay, now let's go to the next blocks. So how can we construct the next blocks? So we have to choose a member from the key block which is not, or we have to choose a member which is not present in the key block. So let's say you can see here B is not present. Okay, so we can multiply each and every member of the key block by B to get the second block members. Okay, so let's multiply this by B. So if we multiply 1 by B, we can get the value B. So if we multiply this C by B, we get the value BC. So if we multiply this by B, so that will be A. As why it is A? AB into B basically AB square, but if we get square term, then obviously that letter will be vanished, so only A. Now ABC is basically AC, A B square C. If we multiply ABC by B, so AB square C, that will give the value AC. Similarly, from this key block we just have to choose, or let's say we just have to choose that treatment combination which is not present in the key block. So let's choose A. So A is not present in the key block, and multiply each and every member of the key block by A. So this is A, this is AB, this is A square C and basically C, and this is ABC. So if we multiply this by A, that will be A square BC. So A square will be vanished, only BC. Similarly, for the next one, B is not present in the key block. So this is B, AB, C and AC. And in the last one, you can see that A is not present in the key block, so we can multiply by A, then B, then ABC, and then C. So simple. So this is a question from Delhi University. You can see in that question, like, if 2 to the power 5 factorial experiment is conducted in 2 square blocks of sizes 2 cube each, then the number of treatment combination that can be allocated independently in the key block. Okay, so we have written that 6 points, you can remember that. So I just have written the 6 points. So in the 5th or 6th point, I have written that they are independent. So if we have, let's say, 2 to the power n comma, so let's take this as this. So if we have, let's say, 2 to the power n comma 2 to the power k order model. Okay, so if we have 2 to the power n comma 2 to the power k order model, then there are k independent. So there are k independent treatment combination. Okay, and we have to take this k independent treatment combination to get the confounded effects, and the other effects will be automatically confounded, and the other effects, which are basically the general interaction effects, which will be automatically confounded. Okay, so here you can see that we have 2 to the power 5 factorial experiment. That means we have 2 to the power n is equivalent to 2 to the power 5, and we have 2 square blocks. Okay, each of size basically 2 cube. So size is not important to us. So we have 2 square blocks. That means the total number of blocks is basically 2 square. Okay, so the value of 2 to the power k is equivalent to 2 square. That means the value of k, is basically 2, and we know that we have k independently treatment combination or independent treatment combination. Okay, so that's why the answer will be A equal to 2. Okay, so the correct option is basically A equal to 2, or A means the option A, which is 2. Now let's go to the next problem. Now in this problem you can see that in, so here let's say in 2 to the power 4, so here 2 to the power 4 factorial experiment conducted in 2 blocks, okay, of 8 runs each. Okay, now the key block is given to us. So that's the important part. The key block is given to us. We just have to find the confounded effect. So you just can see that the key block is 1. So this is nothing but 1 AC, CD, then AD, then B, then ABC, then BCD, and ABD. Okay, so this is my key block. Okay, now we just have to check that among these 4 options, which one has no common or even number of common with the key block members. Okay. So let's start with ABCD. So you can see that ABCD, so obviously this B, so ABCD cannot have even number of common member with B, as ABCD and B has odd number of common member. Okay, so ABCD and B cannot have even number of common member, as the common member is basically B, and which is only 1. So only odd number of common member. So first option cancelled. Now let's go to the second option, which is ABC. Okay, so ABC, we can see from this part, ABC is here. So ABC is present in the key block. Okay, so if ABC is present in the key block, ABC and ABC cannot have even number of common member, as ABC and ABC are basically odd number of common members or odd number of common letters. Okay, so the second option is basically cancelled. Now let's check the third option, which is ACD. So let's go from the first one, ACD. So obviously with AC we have even number of common member, with CD we have even number of common member, which is CD. Then AD, obviously we have even number of common member with ACD, and B, So with B we have no common member. Okay. Then for ABC we have even number of common member. For BCD we have even number of common member, and for ABD we have also even number of common member. So ACD, you can easily identify that ACD and ABD has even number of common member, and those members are basically A and D. Okay. So obviously ACD satisfies all the conditions. Okay. So that's the manual checking procedure. So you need not to calculate anything. So obviously ACD will be the correct option. So ACD will be the correct option. So the correct option will be ACD. Simple. Now let's go to the next problem. So now in the next problem you can see that we have 2q factorial experiment in blocks of 4 plots. Okay. And we just have to find the confounded effects. So these are the 4 options, you can see that. So these are basically the 4 options, and we just have to find the confounded effect. Now if we just check in the key block, so you can see in the key block, so how can we check that which effect will be confounded? So the confounded effect has even number of common or no common with the key block member. Okay. So that's why let's start with the, let's say, PK. Okay. Or you can choose like, so don't go with the options, so just try to check that which effect is being confounded in the first replicate. Okay. So we can see that NP, so NP has common member, so NP is the common member. You can see that NP and NP has even number of common member. NP and NPK has even number of common member. Okay. NP and 1 has no common member, and NP and K has no common member. Okay. So NP and NP, so this is basically even number of common member. NP and NPK, obviously even number of common member, and those common members are basically N and P. NP and 1, so no common member, and NP and K, obviously no common member. Okay. So that's why we can say that NP is the confounded effect in the first replicate. Okay. So we just have to choose option 3 or option 4. As you can see that in option 3 we have NP in the first replicate, and in option 4 also NP in the first replicate. Okay. So option 3 or option 4 will be correct. Now let's go to the next part. So let's check for the NK, that means for the second replicate. So in second replicate you can see that we have PK. Okay. So we have like PK, I'm just removing this part. So we have PK, and if we take, let's say, PK, and if we want to check that PK is confounded or not, so we have 2 options. So obviously, sorry for that. So we have 2 options in option 3 and option 4. So in the second option we have NPK and NK. Okay. But if we choose NK, so if we choose NK, PK and NK, so if we choose these NK, then PK and NK have odd number of common member. You can see PK and NK has odd number of common member, which is basically K. So NK cannot be confounded. So that's why the fourth option, so the fourth option is obviously correct. So you need not to check all the options. So the fourth option is obviously correct. Okay. Now let's go to the next problem. So here you can see that in this question, 2q factorial experiment, there are 2 factor interaction, 3 factor interaction. That means we just have to find the number of main effect, number of 2 factor interaction, and number of 3 factor interaction. So we all know that. So there are basically A, B and C. So 3 factors. So the main effects are A, B and C. The 2 factor interactions are AB, BC and CA, and 3 factor interaction is basically ABC. So that's why the fourth option will be correct, as 3 main effects which are basically A, B and C, 3 2 factor interaction which is AB, BC and CA, and 1 3 factor interaction which is ABC. So that's why the fourth option is the correct option. Now let's go to the next problem. Now in this question, in question number, so in this question you can see that a total yield of treatment of 22 factorial experiment replicated 4 times. So this is given to us, okay, and the values are given to us, basically the values like A0, B0, then A0, B1, A1, B0 and A1, B1. So this is given to us. Now the required value is simple effect of factor A at first level of B. So I just have discussed in the starting of my class today that simple of effect of the factor A at first level of B and the interaction effect AB can be estimated as, so how can we estimate that? So simple effect of A at first level of B, that means B is at its first level, that means B0 happens, and we have to calculate the effect of A, that means presence of A minus absence of A at first level of B, okay. So this A1 B0, so the value of A1 B0 is given to us, which is 32 minus, so A1 B0 is 32 and this A0 B0, so A0 B0 is basically 20, so you can get the value which is 12, okay. So you can see that option B has this value which is 12, so that's why option B is the correct option. Now let's go to the next problem. In the next problem you can see that, so in this question the key block which is 2 to the power 5 factorial experiment is given to us, okay. So the 5 factorial experiment key block is given to us, we just have to find the confounded effects, okay. So always try to take, let's say you can see ABC, so as only one option is correct, so that's why we have ABC and ABC in 2 options, okay. So ABC cannot be confounded, and why? As 2 option cannot be correct, okay. So that's why ABC cannot be confounded completely. So let's start with another some example, like let's say start with some BCE, okay. So let's check that BCE is confounded or not, okay. So BCE is confounded or not, so just check manually. So if we take BCE, so if we take BCE, then 1, so with this 1 no common member, as we have to check with BCE, so for 1 it has no common member. With BC we have even number of common member, with DE we have no common member, okay. So this is even number of common member, this is no common member. With BCDE, with BCDE, so with BCDE we can see that here we have BCDE, so BCDE, so BCE and BCDE has odd number of common member, okay. So this has odd number of common member, so always try to understand that this is odd number of common member. So BCE cannot be a confounded effect, so simple to understand, that means option 2 cannot be correct, okay. And don't try to see these answers, so these answers are most of the time wrong, don't try to see these answers, okay. So option 2 cannot be correct. Now let's check option, so option 4, last option, which is ADE and BCDE, okay. So let's start with this BCDE. So BCDE, so if we start with BCDE, so let's remove this part and remove this part also. So if we start with BCDE, so with 1 we have no common member, with BC as the letters are basically BCDE, so with BC we have even number of common member, with DE we have even number of common member, with BCDE we have even number of common member, with ABD we have BD common member, so that's why even number of common member. With ACD, so with ACD we have CD as common, that means even number of common member. With ABE So with ABE, that means B and E, these are basically common, that means even number of common member. And the last one is basically, you can see that the last one is BCE. So with BCE we have odd number of common member. So that's the problem. Okay, so odd number of common member with BCE. So BCDE cannot be confounded. So that's why option 4 cannot be correct. And why is it is not correct? As BCDE is not a confounding effect, but BCDE is present in the third option also. So that's why third option is not correct. Even the first option, it is also not correct. So all the options are wrong here. Okay, so the question is not correct. Now let's go to the next question. Now in the next problem, you can see that, so we have 2 to the power 4 factorial experiment and the key block is given to us. We just have to find the confounded effects. Okay, so now from the key block we can easily see that AB, so we can easily see that AB, CD and ABCD, these are the confounding effects. Okay, so ABCD and ABCD, so obviously the third option is correct. So the third option is correct option, ABCD and ABCD. Now let's go to the next question. Now in this question you can see that we have 2 to the power 5 factorial experiment consisting 2 to the power 3 blocks of size 2 square each. That means 2 to the power n is equivalent to 2 to the power 5 here, 2 to the power k is equivalent to 2 cube as 2 cube blocks, and the block size is basically 2 square. So 2 to the power n minus k is exactly 2 square. Now the number of independent effect confounded with blocks. So I have told you in the points, I have written the 6 points, and obviously in the 5 or 6 point I have told you that if we have 2 to the power n comma 2 to the power k experiment, then k, we can get k independent blocks. Okay, so you can get k independent blocks. So here k is basically 3, you can understand 2 to the power k is 2 to the power 3, so that's why k is basically 3. So the fourth option, which is 3, so that will be the correct option. Okay, so the independent number of independent effect confounded with blocks, so that is exactly 3, which is the value of k. Now let's go to the next one. So now in this question, in question number 70, you can see that if the layout of single replication of 2 cube factorial experiment, the blocks are given to us and the first block is basically key block as 1 is present. So first block is key block, and we just have to check the confounded effect. Okay, so how can you check that? So first check with the first one. So let's check AC is confounded or not. So if we compare with 1, so AC has no common member with 1, AC has even number of common member with AC, AC has no common member with B, and AC has even number of common member with ABC. So that's why we can surely say that AC has no common or even number of common member with the key block. So AC is being confounded. So that's surely you can say that. Okay, so the second option is correct. Now let's go to the next problem. In this problem you can see that in question number 27 we have 2 cube, so we have 2 cube factorial experiment and we have 2 replicates, so replicate 1 and replicate 2. Now we just have to find in replicate 1 which effect has been confounded, and replicate 2 also. Okay, so let's check that. So the options are like, so options are like ABC, ABC, AC and AB. Okay, so you can see from this part, if we choose, let's say ABC, so if we choose ABC, ABC, so if we just remove this part, so ABC has even number of common member with AB, ABC has even number of common member with AC, ABC has even number of common member with BC, and ABC has no common member with 1. Okay, that means ABC has even number of common member or no common member with the key block. So in replicate 1, ABC is being confounded. Okay, so obviously. Now let's check the next part. Okay, so in next part we can check. So here we have AB, AC, BC and 1. Okay, but in option, so in option we can see that if in replicate 1 ABC is basically confounded in replicate 1, then there are two options like BC and another option is AB. Okay, so BC and AB. So we just have to check that BC and AB are confounded or not. So if we see the second replicate, okay, so the first you can see from this value, like for the first value, so if we take this BC, so the first value AB, we have odd number of common member with BC. Why? B is basically common with AB and BC. So that's why BC cannot be confounded in the second replicate. Okay. Now let's check this AB. So AB with AB, you can see from this part. So you can see from this part. So if we choose AB, so AB with AB has even number of common member, but AB with AC has odd number of common member. Okay, so that's why AB cannot be confounded. But according to the options, so you can see that according to the options, ABC is obviously confounded in the first replicate. So if we choose ABC is confounded in the first replicate, from the option BC or AC, that means option A or option C must be correct, or any one of the option must be correct, but both the options are wrong. Okay, so that's why the complete question is wrong. You can see, as AB and AC cannot be confounded in any one of the replicate, so ABC is confounded in both the replicates. Okay, so you can see that ABC is confounded in both the replicates. So that's why the question is wrong.